I'll begin with a word of prayer. So, Heavenly Father, we thank you for this morning. Thank you for the students with us today. Help us to just glorify you what we do, and pray you to give the students endurance and also understanding, Lord. In your name I pray. Amen. So I'm glad you guys are here today, because what we're covering today is really, really important. I mean, it's probably somewhat rare for me to actually find the time and space to cover, or at least, to test, let's say, everything we did up to this point. I mean, I always inadvertently will select some subset of that to actually put on the test. What I'm doing today, when the rubber hits the road, when we get done building the machine today, I will test every nook and cranny of what we're doing. So it's important that you come to a complete and total mastery of the results that we get to today. Now, the things I'm talking about at the start here, maybe not as much, but they're important as a backdrop to understand the structure of what we're doing and our goals, our aims, and just the general context of where we are. So where we are today is we're going to look at how to solve, and also the theory of the nth order linear ODE. So let me just give you sort of a generic one of those. It looks something like the following. Yn plus, let's say, a n minus 1, y n minus 1, plus dot, 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 plus, let's say, a2, y prime prime, plus a1, y prime, plus a sub naught y equals to g. Okay, so here, this notation means the nth derivative of y with respect to, I guess it's not clear yet, but let's say x for the sake of discussion. Sometimes we'll use t for the independent variable. So, like y prime would be dy dt, right? Oh, I'm sorry, I've already done it. dy dx. Okay? And we say a n minus 1 all the way on a2, a1, a naught are the coefficients of, and I better give it a name. I'll call it star because Oh, yes, thank you. Good point. Very much so. Oh, what a sad marker. Okay. So this guy right here, that's better. I'm calling star, all right? So these are the coefficients of star, all right? These could be functions in principle of x, all right? Now, the lion's share of our effort will be placed in the case that these coefficients are all constants. If the coefficients are all constants, it's said to be a constant coefficient nth order linear differential equation, right? So chapter 4 in your book is mostly about the case n equals 2 constant coefficients, all right? Now, the g over here, this guy, this is called the forcing function. Forcing function, or inhomogeneous term. And so if g is identically equals to 0, in other words, if g is always 0, if it's just this stupid 0 function, then star is homogeneous. All right? Otherwise, if at even one point g of that point, let's say t naught, is not equal to 0, all right, then star is non-homogeneous. All right. Later in the course, we'll learn how to treat the case that g is discontinuous. That's interesting to you, especially electrical engineers, because you guys like to think about switches. They're these things we used to have on the wall that you could turn the lights on and off with. Once upon a time, we had these things called light switches. I mean, we've moved past that as a society now with all these stupid... Anyway, sorry, I miscontrol. Anyway, this is the nth order linear OD, all right? Now, before we do anything else, we should find a better notation for it, all right? So if L, all right, is equal to d to the n plus a to the n minus 1 d to the n minus 1 plus da-da-da plus a1d plus a naught, then we can write star as L of y equals to g. So this L I just wrote down is called a differential operator. All right? Operator. What's an operator? An operator, in the usual language in here, is something which takes in functions and gives you back functions again. You've already been working with operators in Calculus 1, right? The derivative is an operator. You feed it a function, what comes back out? A new function, right? The derivative function. And so this notation, like d to the n minus 1, just means n-fold operations of the derivative, one after the other, right? It means composition. N-fold times or n minus 1-fold times. And anyway, I will explain more about the operator calculus as we go on today. Let me just stop there for the moment and just leave it at that. But this is another notation for the differential equation. And so the fundamental property of this operator is it's linear. It's a linear operator. What that means, guys, is that L of C1y1 plus C2y2 is equal to C1 L of y1 plus C2 L of y2. This is true because this operator is formed by successive multiplications, additions, and just differentiations. Well, differentiation, the sum of derivatives is the derivative of the sum, and you can pull constants out of a derivative. You can also pull constants out of a second derivative, or third or fourth. So you put that all together, you get linearity of this operator. This is really, really nice because it gives us a simple theorem, right? One of the fundamental theorems that I can point out even at this stage, little theorem, the linear combination of solutions to L of y equals to 0 is, again, a solution. So if you add homogeneous solutions together, you get another homogeneous solution. Let me prove this for you. I guess the real issue for you guys, in fact for anyone, is what does this words linear combination mean, right? What do we mean linear combination? What's this mean? So if we have L of y1 equals to 0 and L of y2 equals to 0, all the way on out to say L of y, let's say k of them. Okay, suppose we have k solutions to this homogeneous differential equation. Then, if you look at L of C1y1 plus C2y2 plus dot 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 plus CKYK. All right. This, what I just wrote inside the brackets, this object right here, is a linear combination of the solutions. When we say linear combination, we're just saying add them together, add multiples of the things together, right? Constant multiples. This is a linear combination. But the beautiful thing is, since L is a linear operator, it takes the linear combination to, well, a linear combination in the following sense. I mean, this, you can pull the C1 out, you get L of Y1, I'll skip the second one if you don't mind, plus dot 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 plus CK L of YK, like that, using, so I define linear operator in terms of having linearity of two things, but if you get two things, you can easily prove that that extends to n things or k things by induction if you like, but I'll just claim it because you guys believe me, right? It's not surprising. If you do it for 2, you can do it for 3. Anyway, the point is, since L is a linear operator, I can pull the constants out, I can break up across addition, but then what are we assuming about each one of these homogeneous solutions? They're all what? They're all solutions, right? So they all go to 0 since they're homogeneous solutions. And so in total, we get 0, which shows you that the linear combination of homogeneous solutions is, again, a solution. We saw this yesterday and even the first day with our C1 cosine plus C2 sine solution for y prime prime plus y equal to 0, right? That's an example of this theorem, right? Yeah, before I get lost in the clouds here, let me just bring us back down for an example. Y prime prime plus y equals to 0. In operator notation, this is d squared plus 1 acting on y equal to 0. And we saw that y equals to c1 cosine of x plus c2 sine x. Solved it. Right? But here, the L, all right, L is d squared plus 1 for this one, all right? And d is d dx in my, although it's not clear from the original. I probably should call that example 1. It's
so can L be applied to the y?
Yeah, L could be, I mean, I'm using L as sort of a generic label for the operator which defines the differential equation. Yeah, sure, let's look at a different one. I'm very excited. That was a question. It's taken 3 days. But you guys asked the question. This is very exciting. Let's see here. Y prime prime plus x y prime plus e to the x times y equals to 7 there. So like here, this is really, you know, d squared dx squared, right? Acting on y plus x times d dx acting on y plus e to the x times y equal to 7. See, so you can rewrite this as like d squared plus x times d plus e to the x times y equal to 7. And that would be your L, yeah. Again, I'm going to talk more about how we do calculus with operators as we go on today. I just have a few general theorems I got to get out of the way before we can get to that. I mean, that's the line. Most of what we're doing today is studying properties of linear operators. Does that make sense? Okay.
This is kind of like just like the coefficients.
Right. Yeah, I mean, I guess the real question here, and I try not to get into this full force yet, but xd, what's that mean when that acts on a function? This means that you take x times d df. Well, to be more explicit, and annoyingly, I mean, df dx, fine. Right. This is kind of a boring one. E to the x acts on f. That's just equal to e to the x times f. I mean, this is multiplication. the multiplication function. It's really, the multiplication operator is not a terribly exciting operator, but it's also important to our work. Okay, so our first and important theorem, linear combination of homogeneous solutions is homogeneous. Let me just give me a second here so I don't go down too inefficient a path. I try to roughly follow my notes too, so I want to try to put the theorems in the order that they're in the notes, more or less. Come on. Wake up. All right. We're currently in section 3.1. At the moment, I've given you the definition, a word about notation. The next big theorem we have is theorem 3.1.2, which is the existence and uniqueness theorem. Don't worry, I'll just write it. I won't prove it. I mean, the proof of it. Well, that's harder, but here it is. The nth order linear ODE star, all right, for which a sub naught, a sub 1, all the way out to a sub n minus 1, and g are continuous. What's that mean? If you have those are all continuous, all right, on some interval. So this is a connected subset of real numbers. So it could be the whole real line. It could be like a ray out to infinity. It could be the open interval from 3 to 7. I mean, whatever. The point, basically, that means that these functions are pretty well behaved. They don't have jumps, you know. They don't have vertical asymptotes and stuff in here. They're nice. Nice enough functions. You wouldn't mind being their neighbor or whatever. Anyway, so if you have all that, and at x naught an element of I, you're given that y of x naught equals to y naught, y prime of x naught equals to y1 on down the line, all the way up to the n minus 1th derivative at x naught is equal to y sub n. So this is initial conditions, all right? So what I'm saying is, suppose you're given an nth order linear differential equation, all the coefficients are continuous on some appropriate subset of the reals. You got a point in that subset where the position, the velocity, the acceleration, all the way up to the n minus 1th derivative, they're all specified, all right? You have all of that, then there exists a unique. Unique solution, we might call it y equals to phi, for which L of phi of x, right, is equal to g of x for x and I, and, you know, phi satisfies, let's say it fits the initial data. What would I mean by phi fitting the initial data? I mean, you know, phi of, what's phi of x naught is going to be what? Phi prime of x naught is going to be what? I feel like I should have projected this. I'm sorry, I seem to have wasted our time. You'll forgive me. So fitting the initial data means that the solution, which I'm using phi for at the moment, phi of x naught should be what? It should be the given y naught, you know. Phi prime should be y1 and so forth and so on down the line. All right. So this is the existence and uniqueness theorem. It says that the nth order initial value problem not only has a solution, it's got one solution. All right? So that's nice. I have a few examples in the notes I'm going to skip over. Our time is limited. Now, to understand this solution, we have to talk about something called linear independence, all right? So, definition. F1, F2, Fn are linearly independent on I, which is some subset of the reals, if C1 F1 plus C2 F2 plus plus C and Fn equals to 0 implies C1 equal to 0, C2 equals to 0, and on down the line. I'm being sneaky, all right? This equation I just wrote is a functioning equation, all right? So like, to be completely honest, what this really is C1 F1 of x plus C2 F2 of x plus plus Cn Fn of x equals to 0 for all x in the interval I. So linear independence of a set of function is always properly measured with respect to some interval of real numbers. When you look at differential equations books, this is not always emphasized. Sometimes they'll just say things like, and I'll do this too, I'll say things like sine and cosine are linearly independent. Well, strictly speaking, you should be like, with respect to what interval? That's relatively harmless because the interval doesn't matter. There are other functions which are linearly independent on one interval but linearly dependent on another interval. Like, so, anyway, you can read more about that in the notes. I'm going to move along here. Now, let's see here. So, suppose we have a set of linearly independent functions. Now, all that's saying is they're not, I mean, okay, so like, over here, you can prove sine and cosine are linearly independent. We'll do that once we develop the tool here shortly. Why would you want linear, let me just talk, before we get to that, let's just pause for a second here. Why do we care about linear independence? Well, it's what we need to make sure that the solutions we're getting are not redundant. All right, so like if I had, instead of this, if I wrote, say, you know, like y, let's say y bar equals to b1 cosine of x plus b2 3 times cosine of x, you know? Well, this would be dumb in the sense that, like, that wouldn't be a general solution. I mean, it looks like I've got two solutions. I've got a constant b1, I've got a constant b2, right? But the thing is, the two functions, which I'm using to build my solution, they're not independent. They're not really giving me all the possibilities. You know, if I want to have a solution for that example 1, which has the position being 0, but the velocity being 1, I don't think I can do it. See, the only way you can get position 0 with y bar is to set both b1 and b2 to be 0. Right? To get position to be 0 at time 0, I mean at x equal to 0, and to get velocity, well, velocity, I don't know, I'm using x for the independent variables. It's cramping my style. Here, I'll fix it, t. Now these comments will be less weird. So, you know, if I want position to be 0, it's going to force b1 and b2 to be 0. On the other hand, if I want position to be 0 up here, what do I get? I just get c1 is 0. I'm still left with this c2 sine piece, right? And when I differentiate it, I get c2 cosine. So I can fit that initial condition, right? I can have position 0 at time 0 and velocity 1 at time 0. That's possible with what I wrote down and what we derived yesterday. It's not possible with y bar, right? So it's important to maintain linear independence of the functions you're finding to build the general solution, because if you don't, you simply won't be able to address all possible initial conditions, right? All right, I'm getting a little bit ahead of the story. Let me get back on track here. So suppose we have a set of linearly independent functions, right? This is kind of a drag, right? To actually work this out, like I give you 10 functions, I say, are they linearly independent? Okay, honestly, that's always a bad question. But suppose I have 3. You know, to actually work out the algebra here, that's weird. I mean, it's not nice for you guys. But what we can do is just take this. Suppose they're linearly independent, right? What happens? We can differentiate this, right? Let's suppose they're functions of x. What happens when I differentiate this equation? I get the linear combination of the derivatives of the functions also has to be 0, right? And then differentiating, I can't just stop at one differentiation, differentiate again, right? Right? And then just keep differentiating, and what do you get? If we want n of them, I'll get all the way to the n minus 1th derivative, right? So if you look at it, if you ignore the blue comment there, we have n equations in n unknowns. Now, how many of you have had Math 221 already? 1? So the rest of you have no linear algebra at all? Oh, unfortunate. Well, it's time to learn. So you remember from high school? No, not anymore. It's a lie. But in principle, there's this thing called high school where you might learn to multiply matrices. Dr. Sperano tells me it was the case once upon a time. I'm a homeschooler. What do I know? But he says that about everything in high school. That's not a terribly meaningful comment for Dr. Sperano. Well, all right. Anyway, so if you look at this, you'll get an n by n matrix. Don't worry, I'll do some examples that'll make it better, I think. And you can, it's basically this n by n matrix times this column vector is equal to 0. Now, technically, this is at each x in the interval I that we're talking about. This means element of. I'm not snowing any of you over with that, am I? Okay. You know, if there's ever a question like that, you ought to ask it, yeah? These are just notations. It's not. Wait. Okay, so anyway, what we have is matrix times column vector equals to 0. One of the central theorems of linear algebra is that if the only solution to this is the 0 vector, and that's what we're assuming here, right? This equation implies that all the coefficients are 0, right? If that's the case, what has to happen is that this matrix is what's called an invertible matrix. It forces this matrix of functions to be invertible at each x in I. Now, there's many ways to look at that, but the most convenient calculational way for us to look at it is then that the determinant of this matrix has to be non-zero if the functions are linearly independent. So, in fact, when we definition, the Wronskian, W, and I'll use y's because my f's are ugly, y1, y2, yn at the point x, all right, it's equal to the determinant of this kind of matrix. So we do y1, y2, yn in the first row, and then we do derivatives in the second row, and we do second derivatives in the third row, and so forth and so on, until we get to the last row where we get the n minus 1th derivative, right? So what this derivation shows you is that if the functions are linearly independent, all right, on I, then the Wronskian of those functions must be non-zero on I. So a nice calculational tool we can use to check up on linear independence is the Wronskian. We can just calculate the Wronskian of the functions. If it's 0, hey, they're linearly dependent. Okay, that's not true. But if they're non-zero, it's linearly independent. Something annoying happens with the converse direction because you could have different linear dependencies for different x, and then you would still have linear independence. It's subtle. Now, let me not talk too much about that subtlety because we're interested in solution sets, all right? And for solution sets, there's a beautiful result called Abel's formula. And Abel's formula basically tells us what the Wronskian is in terms of something having to do with the differential equation. Let me get to it here. Well, I'm going to project something here in a second. Before I do that, though, let's actually do an example of these. Because you guys know determinants from Calculus 3, you just might not remember. Let's start with something simple. I think if I do 2 carefully, we should be okay. So let's start with sine cosine. The Wronskian of cosine and sine. So we'd look at the determinant of, we put cosine, we put sine, and then derivative of cosine is what? It's minus sine, and derivative of sine is cosine, right? How do you take the determinant of a 2 by 2 matrix? You do, generically speaking, if we have A, B, C, D, how's it go? We do A times D minus B times C, right? Anyway, that's the definition of a 2 by 2 determinant if you didn't know it already. And so this gives us cosine squared x plus sine squared x. Hey, but that we know is what? That's 1, right? As you know, hopefully I don't have to argue with any of you about this. 1 is not equal to 0. Consequently, sine and cosine are linearly independent for any subset you can think about of the reals, actually. Right? I mean, so that's why it's okay to say sine and cosine are linearly independent, because it's harmless. I mean, whatever interval of real numbers you think about, it's going to be true. Let me stop talking about the interval dependence of linear independence, because that's really beyond this course. It's just, to be honest, I can't help but say a word or two about it. So I'll shut up about that. Here's another one. This one, you might think, if we have e to the x, right, and we have x e to the x, and we have x squared e to the x, I may regret this, you might be tempted to think that these are linearly dependent, right? Because if you look at x e to the x, what is it? It's a multiple of e to the x, isn't it? It's just x times it. But the thing is, we talk about linear independence with respect to real numbers. So like the multiple that's going on there is not the kind of multiple we're talking about for linear dependence. See here, these are constants. X is not a constant, and we're going to be able to show that those are linearly independent functions. All right? So let's see here. We would calculate the determinant. So we put e to the x. Ooh, I'm going to regret. Ooh. This is going to sting a little. I guess it's okay. Differentiate one time. That's still okay. That's 1 plus x e to the x, right? And over here we get 2x plus x squared e to the x. Hey, why did I agree to this? I'm going to regret this example. What example were we on? This is example 2, 3? Yeah. This is example 4, I suppose. Hey, I can do the derivative of the first column. And we got to do product rule is the thing, right? So if you differentiate this times that, we get what? We get 1 plus I think we get 1 plus 2x, yeah? No. No, we get 2, you guys help me out here. I don't want to write out the steps up here. That's bad, but it's true. Is that right? I think that's right. And then this one is harder for me to do in my head, but I'll try. So we'll get 2 plus 4x plus x squared e to the x, yeah? Did you guys get that? All right, now, how do you calculate the determinant of a 3 by 3? So let me tell you something nice about a property of determinants is it has what's called multilinearity. I mean, you can factor constant. If you have some constant factor in a column, you can just pull it out. So I've got an e to the x here. I've got an e to the x over here. I got e to the x over here. It turns out by properties of the determinant, I can pull out e to the x 3 times, e to the x cubed. And then I'll have determinant of 1x, x squared, 1 plus x, or x plus 1 if you like, x squared plus 2x, fine, x plus 1, it's bothering me. I'm an idiot. 1 x plus 2, and x squared plus 4x plus 2. All right, at this point, I can do it, I guess. All right. If you don't mind, I'm going to work up here. So do you guys know how to take a determinant of a 3 by 3? What we do is it's just like the cross product, right? So start with this 1 and look at everything that's not there. So this is going to be, we still have that e to the x cubed outside, which we could rewrite as what? Let's be civilized. That's e to the what? E to the what? E to the 3x, yes. And then we're supposed to do the determinant of everything that's not in the first row and column, which is this x plus 1, x squared plus 2x. Oh, this is awful. X plus 2. I'm too far in, I can't bail. Ah. This was for good pedagogical reasons for the totality of this lecture, but it's hurting me right now. And then x, so I do minus minus x times the determinant of everything that's not in the first row and second column, which is x squared plus 2x, x squared plus 4x plus 2, and then the x squared. And then we're supposed to multiply that by the determinant of everything that's not in the first row and third column, which is this guy. And then we got to close that big bracket I started up there. So now it's just algebra. It's relatively straightforward, partly painful algebra. E to the 3x. Does that factor or anything that makes it easier for me to write it? I don't know. It's x plus 1 times x squared plus 4x plus 2 minus what? Now, this is what? This is x times x plus 2, isn't it? Right? So when I multiply these two, I really have minus x times x plus 2 squared, right? And then minus x times this stuff, which is x squared plus 4x plus 2 minus x squared plus 2x. And then, last but not least, plus x squared, and that's x plus 2 minus x plus 1, parentheses are our friends. Man, I should have made this a homework problem. Oh, you guys don't have homework. Oh, but you have a quiz. Ask a quiz. I should write that quiz. Let's see here. Where are we? See, I think there's some cancellations here, right? So I believe, can you tell me which one? Where? Ah, see it? I want to say this is x times x plus 2. You got two minuses, but against this one minus. So this guy and that guy are natural enemies. The other thing I think that would be minus x times that. Up here there's plus x times that, right? So essentially this x would cancel with that term. So I've lost all my red terms, and at this point I have e to the 3x, and I've got an x squared plus 4x plus 2, and down here, oh, the x's cancel, yeah? And this is just x squared, right? The green stuff simplifies to x squared. And then, this is a great time to introduce one of the very important algebraic ideas in this course. In fact, this is not a new idea for us, I'm hoping. But if you complete the square here, that's x plus 2 squared. Oh, that was not helpful. Sorry. I'm an idiot. Let's see here. So this is 2x squared plus 4x plus 2. I should have factored the 2 out, right? Aha. Right? And that's actually x plus 1 squared, right? So we've got 2e to the 3x times x plus 1 squared if I didn't do something wrong, which is debatable. I mean, I did a lot of steps here. I hope you understand the larger point is to take the determinant of a 3 by 3 matrix. We do the same thing we did in Calc 3, like the cross product pattern, right? And if it's non-zero, that proves linear independence. If it's 0, well, that doesn't prove anything just yet. Let me show you a theorem which helps us out. So my goal here is to wrap up all this theory stuff, and then we will, after the break, dive into the operator calculus, which might still seem theoretical to you, but it's actually how we solve problems. This really, at the moment, is just the backdrop we need to understand what we're doing. We're well on our way. Almost there. While we're waiting for this to load up, the trouble with things that are not solution sets, check this out. I could have the function x and the function absolute value of x. These, if you calculate the, well, I should say x squared and x times the absolute value of x, these are both differentiable. I don't know if you've ever seen this function before. X times absolute value of x, it's kind of a funky function. It's two parabolas just glued together like that. The derivative of this function exists, but is not itself differentiable. This is a once but not twice differentiable function at 0. The derivative basically looks like that. So the derivative of x, absolute value of x, is, I think, maybe 2 absolute value of x, I forget. But so you can't take 2 derivatives, right? But you can take 1 derivative. And if you calculate the Wronskian of this thing, I won't go through the details, but it's pretty easy to see that it's 0 for all x. But these functions are not the same function. They're not linearly dependent. Like if you look at the graph of x squared, it's this, right? If you look at the graph of the other one, x, absolute value of x is that. They should be overlapping, sorry. Limits of my artistry, you know? These are not linearly dependent functions, and yet the Wronskian's everywhere 0. The reason is that they're linearly dependent this way here, but just multiplication by -1 over here. So it's subtle. You can have the Wronskian everywhere 0 and yet have linear dependence of your functions. Excuse me, independence of your functions. I can't say it straight. Now, this is annoying. And I mean, research mathematicians wrote papers about this in the late 19th century. All right? So it's a hard thing that I'm talking about. And it confuses mathematicians even nowadays, some. But the wonderful thing is, we have this theorem that gets us around it. This is part of the theorem anyway. I'm trying to speed through this part of it so that we don't, I need to make sure we have enough time to talk about what comes past here. So this is we just argued this. If the Wronskian's non-zero, then the set of functions is linearly independent. Oh, thanks. On the interval. On the other hand, if there exists a point such that the Wronskian 0, then the set of functions is linearly dependent on I. Now, what's the difference between this set of functions and that set of functions over here that I went through before class? This is in fact not a solution set. You cannot give me a linear differential equation which has x squared and x times absolute value of x as a solution set. You just can't do it. This is special. I'm assuming not just that they're arbitrary functions, but that they're solutions to a linear differential equation. That's the difference. For solutions, we do get a converse. We do get that if the Wronskian is non-zero, even at one point, it's linear. I mean, if the Wronskian is 0, even at one point, rather, we have linear dependence of the functions. So Wronskian is like, as long as we're dealing with solution sets, which is what we're interested in, the Wronskian's the ticket. All right? And here's the derivation. The Wronskian is, I've put this on tests before. This actually makes a nice test question, what I'm about to look at here. So W is y1, y2 prime minus y2, y1 prime. Someone's walking on the roof as usual. Sorry about that. Anyway, so call that thing W. If you look at W prime, it's this. You notice some of these things cancel, right? Like, what cancels here? Something cancels. Oh, this one and that one, right? Gone. So you're just left with y1, y2 prime prime, y2, y1 prime prime. All right? I'm looking at the n equals 2 case. All right? So if they're both solutions to this differential equation, that means we can rewrite y prime prime in terms of y prime and y and the coefficients, like so. And if I take these and I plug them back in here, I get w prime is equal to this and that. But some things cancel out here. Like this. We get y1, y2 minus y2, y1, same coefficient, but minus minus gives me plus. So this piece and that piece cancel, and I'm just left with minus a1 over a naught y1, y2 prime minus y2, y1 prime. But that's the Wronskian again. See, so what we find is that the derivative of the Wronskian is proportional to the ratio of the coefficient functions, a1 and a naught, times the Wronskian again. But hey, we already know how to solve this kind of thing, right? We can separate variables and solve this thing. No problem. And so you do that, and that gives you Abel's formula. Abel's formula says that the Wronskian is some constant times the exponential of the integral of the ratio of the coefficient of y prime and the coefficient of the 0th term in the linear ODE. But this is a very powerful formula because what that says, if you look at this formula, like, just think about such a formula. If your friend tells you that the function is some constant times an exponential, if that's 0 one place, that forces the constant to be 0. So it has to be 0 everywhere, right? So this formula is either 0 everywhere or it's non-zero everywhere. So that forbids this kind of stuff from happening, basically. Anyway, you're like, well, that's just the second order case, but you claim the theorem's true for the nth order. That's true. Here's the proof. I'm not going to go over it, but it is true for the nth order as well. It just requires, like, this is the hardest calculation in my notes easily, all right? But it's still true. Abel's formula is true for the nth order case just as much as the second. Now, I would not test on this, obviously, right? That would be unfriendly. So that brings us to some important terminology. The fundamental solution set for a linear ODE. What we want is a set S of n functions, all right? These functions have to be solutions. Now, they don't have to be solutions to this. Like, f could be non-zero. We don't care about f. The fundamental solution set actually is a set of homogeneous solutions. So it solves the corresponding homogeneous problem. Basically, set f to 0. These guys solve that, all right? And one other thing, for them to be a fundamental solution set, they have to be linearly independent. In other words, if we take the Wronskian of them, it has to be non-zero, all right? In fact, it has to be identically non-zero, which is what worries me about this. I got to think about this, guys. I want to, well, I must not. There could be an arithmetic mistake in this example. I'm just saying that, all right? And so here's the theorem. If we have an nth order linear differential equation with continuous coefficient functions on an interval I, then there exists a fundamental solution set. And the proof just uses the theorem I already wrote down. You just look at this particular initial data set, your first solution, let its position be 1 at x naught, and its velocity and acceleration and so forth be 0. And then, like, your second solution, instead of you make this 0, you make that 1. Your third solution, you make this 0, 0, and that 1, and so forth. So if you do that, then you'll get a matrix that if you've had linear algebra, you'll recognize. So if we have that initial data, then the Wronskian at x naught looks like this. This is the identity matrix, which is part of this definition of the determinant is made such that the determinant of the identity matrix is 1. So if the Wronskian at x naught is 1, that forces the Wronskian to be everywhere non-zero, and consequently we have linear independence of those functions which exist by the existence of uniqueness theorem, and consequently have a fundamental solution set. So there is always a fundamental solution set to find for the linear differential equation that we have over there. So our job is finding it. How do we find this fundamental solution set, all right? So the general solution, if we have a homogeneous problem, L of y equals to 0, then the general solution looks like this, where the y1 through yn are a fundamental solution set. They're a set of n linearly independent homogeneous solutions. That's it. So if you can find them, right, what this theorem says is that once we look at example 1, when we find cosine and sine, they both solve y prime prime plus y equal to 0, right? We observe that they're linearly independent. So this theorem says then, hey, C1 cosine plus C2 sine, that's it. End of story, game over. We don't have to worry that there's something else out there we're missing. This theorem says that that is the general solution. Once you find a fundamental solution set, you can construct the general solution to the homogeneous problem. I'll let you read the proof, that's fine. And then what I won't be talking about too much today, maybe at the very end I'll do a little bit on this, but tomorrow will be all about the particular solution. The particular solution is what it sounds like. It's a particular solution. So it actually solves L of y equals to f. So L of yp equals to f. That makes, I mean, if you plug it in, it actually solves the differential equation. And if you have that, then you add the particular solution plus the general solution to the homogeneous problem, and that gives you, in fact, the general solution to the non-homogeneous problem. All right? That's tomorrow, is we're going to learn methods to calculate the y sub p. All right? But you see, to solve the non-homogeneous problem, we first must solve the homogeneous problem. We first have to learn how to find these y1 through yn for, for appropriate differential equations. All right. So that brings us to operators in calculus, and more importantly, I think we have earned a 10-minute break. So let's pick up again here at 11:55. All right. Oh, and if you have questions about homework after break, we can start with that actually. Yeah.
I just want to ask.
Or you can ask me now if you want.
Well, for the one we did there, like on the Wronski for it, what does that mean? So
Oh, well, the thing that's worrying me here is that if I put x equal to -1, then I get 0 here, which makes me think maybe I did something wrong. It was more obvious for sine and cosine, we got 1, right? But Abel's formula encourages me to think that I shouldn't be able to get, I shouldn't be able to get 0 at -1. So I think I made a mistake somewhere in that calculation. I want to believe I made a mistake somewhere in that calculation, but
even if you didn't, like, what does that mean if it does equal somewhere, 0 somewhere?
it means they're linearly dependent. If you have functions which are a solution set, if each one of the functions, if you have, I gotta be careful. If we have n solutions to an nth order problem, and their determinant of the Wronskian of those functions is 0 at even one point, they're linearly dependent. Now, if I have 2 solutions of a third order problem, and I calculate the Wronskian of those, and it's 0, it doesn't mean anything. There's fine print here, and it's only for solution sets, because for non-solution sets, it's just awful. Yeah. Linear independence, easy. If it's non-zero, we got linear independence, good to go. Linear dependence, there's a subtlety there. All right, I shut up. You can hit it, don't mind. Thanks.